Okay, so continuing with numerical integration, um, where I left off last time was showing you Newton-Cotes rules, which are interpolatory quadrature rules. So quadrature rules based on polynomial interpolation, in which the nodes are equally spaced. And before I get into today's topic, which is composite quadrature rules, I'm going to spend a little more time on Newton-Cotes rules by showing you something in MATLAB. Okay. Now, screen share going. Let's see. Okay. Um, yeah, okay. This is what I wanted here. Now in the first section in the book on numerical integration at section 9.2, that deals with general interpolatory quadrature. One of the functions that you would be writing as part of a homework for that section is um, is this one, interp quad. And actually, I want to get the actually, hold on. I want to modify how I'm sharing because I actually want to share my whole desktop because I'll be looking at multiple things. Okay. If we look at this section, there's a few MATLAB functions that the homework calls for. Okay. So this is the first one, polydef int, which is this is very, very short. All it has to do is take in a vector p, which consists of polynomial coefficients in the usual way that MATLAB works with polynomial coefficients, and then returns the definite integral of a polynomial represented by p on the interval AB. And here you use MATLAB's polynomial functions for certain polynomial functions that MATLAB has, and those are listed toward the end of the tutorial that make this function quite easy to work out. And then this problem builds on this one, and another function that was from a previous assignment, make Lagrange, to implement this function, interp weights. So what I showed you last time for any interpolatory quadrature rule is that once you've chosen the nodes, which would be in the vector x, then there's a formula for weights. It's just the integral of the Lagrange polynomials corresponding to the nodes and on a specified interval AB. So, so once you have chosen whatever nodes you want for your quadrature rule, then this function will give you the weights. And then that function is used in this one, interp quad. So this implements a general interpolatory quadrature rule. So what you specify are function f you want to integrate, the interval you want to integrate it over, and then you specify the nodes. So this can be just some vector of nodes that you choose. And so this function will carry out interpolatory quadrature of this function on this interval using these nodes and the weights that go with them. Okay. Now, what I'm going to do now is, so I'm not going to show you this function because it's assigned for homework. I don't want to give that away, but I am going to use it for for implementing a general Newton-Cotes rule. So the only thing that the Newton-Cotes part is adding is that the nodes must be equally spaced. So here I have the code for quad Newtoncotes. Okay, so this was exploration 9.2.4. This problem actually is an exploration. It's just one that I did not assign. So I'm fine with showing you the code for it. And it's 9.3, check. 9.3.2. Okay, so here the parameters are a function if you want to integrate, the interval you want to integrate on, and then you specify the number of nodes for your Newton-Cotes rule. Now, here I specify that the rule is closed. So the endpoints A and B have to be included among the nodes. So what I need to do now is get a vector consisting of all of the quadrature nodes. And it's just going to be equally spaced points on the interval AB. Now, the easiest way to do that, one that you see before, is this one. I'll briefly uncomment it using linspace. So you specify you want equally spaced points between A and B that include A and B, and then and you want n of them, since n is the number of nodes. I also want to show you how else it can be done using a colon operator. So you get a spacing. So the spacing would be the width of your interval, b minus a, divided by n minus 1. And the reason for that is you're going to have n points in total, but a and b are two of those points. So therefore, you're going to have n minus 2 nodes in the interior of AB, and those n minus 2 points will sit between n minus 1 subintervals. So this is how many subintervals you'll have of AB that are created by choosing the nodes. So this is the spacing between each node, b minus a over n minus 1. And then to get a vector of the nodes, you take that spacing and then multiply it by the indices, so 0 to n minus 1. And then you add a to it. So you can see, for instance, for the index 0, you're just going to get a. And then if the index is, so if you think of the nodes as being numbered from 0 to n minus 1, so for the index n minus 1, that will cancel with this, leaving you b minus a. So then you get a plus b minus a, and therefore you get b. All right. And then once you have the nodes, you're just delegating. It's interpolate that's going to do all the real work. So you're using an interpolatory quadrature rule to integrate f over ab, and then you have your nodes. So then interpquad will then call the function I mentioned earlier, interpweights, to compute the weights for interpolatory quadrature by integrating the Lagrange polynomials, and then the quadrature rule will be evaluated. And a lot of what's going on with the homework problems in this chapter, dealing with integration, is making use of other functions. So each function by itself may not have very much code, but this is how code is best written. That you're breaking it down into subtasks, and you have a function for each one, because that way code can be efficiently reused. Any questions about this code before I go ahead and use it? Okay. Oops. Okay. All right. Okay. As a reminder, when you use if you want to use a diary, for instance, for assignments, I recommend when you specify file name, add this .txt extension. So that way, Canvas will open the file. Like if I click on it in Speed Grader, if I download the file, I can certainly open it. But it's easier to go through and just click on files in Canvas, and then it shows them to me. But Canvas will not open the file unless there's an extension. Okay. So what I'm going to do is carry out Newtoncotes Quadrature for this integral of e to the x on the interval 0 to 1. So the exact value of this integral is with a number e minus 1, because the integral of e to the x, of course, is e to the x, and you have e to the first minus e to the 0, which is 1. So we get e minus 1, which is approximately 1.718. Okay. So that's the answer that we're looking for. Okay. Now, so for a simple example, I'm going to do, okay, quad Newtoncotes. So if you look at the code, the first parameter is a function, and then we have a, then b, then the number of nodes. Now, the first argument must be a function handle. So if you have a function implemented as an M file, then you would put an @ sign in front of it to indicate you're passing a function handle. So here I'm using a built-in MATLAB function exp. So so by specifying @exp, I'm passing the function handle for exp. So then when the function is called inside the code, it'll invoke this function. And then 0 to 1. And at first, I'm just going to use 3 nodes. Okay, and we see that the answer is pretty accurate. Now, this particular Newtoncotes rule is one that I've discussed previously. This is a Simpsons rule. So how Simpsons rule works? It's okay, 1/6. Dang it. All right. Times function value at the left endpoint plus 4 times the value at the midpoint plus the value at the right endpoint. So if I carry this out, we see it's exactly the same, because that's really what, so a closed 3-node Newtoncotes rule is just Simpsons rule. Okay. Now, presumably, or well, intuitively, you would think that if I now go ahead and carry this out with an increasing number of nodes, that I should get a more accurate answer. Now, there's a lot of decimal places here. It'd be nice to see the error. So what I'll do is save this in the variable and then show the error. Actually, before I do that, I want a variable for the exact value. So that'd be e minus 1. Okay. So now I save this in the variable, and then the error will be the approximation minus the exact over the exact. So now this is what I'll print out, and we want to see, of course, this error getting smaller. But it's already fairly small to begin with, so not bad considering that we're only evaluating the integrand at 3 points. So what happens if I do the same thing except increase the number of nodes? All right, so we see, all right, it's an increase. Um, and I'll keep going. Oh, big jump there. That's nice. Not so much there. Okay, now, so this is what we hope would happen. And EVX is on the interval 0 to 1 is a nice smooth function. Certainly something that can be approximated by a polynomial. And we see the error continues to go down. Okay. Now, oh, went up a bit, but it's still quite small. But now we see a worrisome trend here. Warnings because of it's using a MATLAB's polyfit, a polynomial interpolation function. Because I'm using more and more nodes, they're getting closer together. So now polyfit uses really the least desirable method for polynomial interpolation. It forms a van der Waals matrix. And I've already pointed out the pitfalls of that. I'm not sure why they use that, but so at least the error is still small. And that's kind of jumping around a bit. And it's getting larger and larger. Those warnings are kind of annoying. So I'm going to turn them off. Okay. Let's just go up to 20 nodes. Oh, that's pretty bad. And if we keep going, things have very much gone awry. Yeah, so the approximations are actually diverging. So, um, so what went wrong? Well, this is something I pointed out last time that once you use enough nodes, some of the weights go negative. And this corresponds to what we've seen happen with polynomial interpolation with equally spaced nodes, that you uh, that that kind of polynomial interpolation at high degree, equally spaced points, produces a polynomial that it still fits the data, but the error can be quite large in between those points. And so it makes sense that if your approximating polynomial is way off, your integral will be way off. And what I can do here is, so I have a function interp weights that computes the weights. So if I just want to compute the weights, okay. So for example, what this function does is I pass a vector of nodes, equally spaced nodes between 0 and 1, and there are 3 of them in this case. And, oh, sorry, I need to check something here. The arguments for interp weights, ABX. Oh, this needs to be 0 to 1. Okay. So here we have the interval 0 to 1. And here are the weights. Now, as I mentioned before, when you have 3 nodes, a Newtoncotes rule, that's the Simpsons rule. And sure enough, these are the weights that we would expect: 1/6, 2/3, 1/6. But then if I keep going, let's say up to 7, there's a nice symmetry to the weights. That's to be expected because we have the same symmetry to placement of the nodes. Okay, but once I get high enough, we start getting negative weights when we have 9 nodes. I pretend they're all positive again, but it's been proven that once you get to 11, anything higher than that, there will always be at least 1 negative weight. Now, the thing is, the weights are supposed to sum to 1, and in fact, they do sum to 1. But because you have both positive and negative weights, like for this example of for 10 nodes, all numbers are pretty small. If you're going to have an average value of 0.1 to all sum to 1, you have to sum to the length of the interval, which is, in this case, 1. But once negatives are allowed, the numbers can get pretty large in absolute value. So, for example, 20, yeah, so, and you have a weight should be between 0 and 1, and they're very far outside of that. And as you increase the number of nodes, it just gets worse and worse. And you get weights from the interval 0 to 1 on the order of 10 to the 7th. It's just crazy. So, high degree Newtoncotes, terrible idea. Questions about what we've seen here? A question was asked last time, what about, instead of using equally spaced points, Chebyshev points? Because it's been known that reduces the error in polynomial interpolation. And I mentioned that is called Clenshaw-Curtis quadrature. So if I want Chebyshev points, and if I recall for you a formula for Chebyshev points, here we go. Okay, so if you have a Chebyshev polynomial of degree k, then these are the roots, and these fall within the interval -1 to 1. So what I want to do now is use Chebyshev points, but on the interval 0 to 1. So that means I have to do some shifting and scaling. So I'll use this formula and then shift them by 1 so that they fall between 0 and 2, and then divide by 2. So then I have Chebyshev points rescaled to the interval of 0 to 1. Okay. All right, so let's say degree 10. So my nodes in this case will be, so I use this formula for Chebyshev points. So cosine 2 times 0 to 9, with zero-based indexing, plus 1 times pi over 2 times the degree. Okay, actually, what I'm going to do here, I'll set a variable for a degree because I want to use this for different degrees. All right, so use XC for Chebyshev. Okay, so these are the Chebyshev points from that formula. And then I'm going to add 1 to them, and then divide by 2. And now that's a row vector. If I make it a column vector, okay, so these are values between 0 and 1. They happen to be in reverse order, but the order of the nodes doesn't matter. And these are not equally spaced. Because notice here they're like roughly 0.15 apart, but here the spacing is much less, and that's what we know about Chebyshev polynomials are clustered near the boundaries. So now if I do interp quad with the exponential 0 to 1, and then these Chebyshev points, and I'll save a result in the variable I. And then the error is relative error in this case. Okay, so let's see what the error is this time. All right, that's quite good. Now that's with 10 nodes. So what if I mean, said before that in the previous examples, um, the error got quite bad once we got up to 20. Um, so if I do the same thing this time, so n equals 20, get the Chebyshev points adjusted to the interval 0 to 1. And then integrate again. Oh, not as bad. But still not what I was hoping for. Um, and if I go to 50, oh, well, that's unfortunate. um, okay. I wasn't actually expecting it. I'm gonna take a look at the weights. All right, this before was for equally spaced points. I use the Chebyshev points that I just computed for degree 50. Oh, sure enough, there are negative weights. Okay. Or let's say for n equal 20. Okay, these are still positive weights, and the result in that case was at least reasonable. But eventually it goes bad. Okay. Um, okay. Just want to check on okay. Let's see what the commentary is um about Clenshaw-Curtis. Is that's something I'm covering and just mentioning that this is what happens when you use Chebyshev points. Um, okay. Ah, so this is interesting. Yeah, because I mentioned, I think I might have mentioned in class last time that the weights um are supposed to be positive. Um, and then theoretically, yes. Um, and sure enough, there's a formula here for weights, and this is something that can be accomplished because of the nice properties that Chebyshev polynomials have. But we saw for a large enough degree that this didn't happen. So the question is, why would that be? When, as far as what we've seen here, analytically, the weights are supposed to be positive. And actually, I can give you an answer to that. Because if I consider the case of, let's say, 50 points, so now I get my nodes, and now what I'm going to do is I'm going to compute a sample Lagrange polynomial, and we saw that the weights for these points were particularly small and then much larger over here. So if I go ahead and pick a Lagrange polynomial, so a Lagrange polynomial will be equal to 0 at all of these points except 1, and then the other one will be equal to 1. So I'm going to generate a 50 by 50 identity matrix, and I'm going to just randomly choose um, a row of the identity matrix, say row 40. So this will have all zeros except the 40th element will be equal to 1. So these are appropriate y values for a Lagrange polynomial. And then I will do polynomial interpolation and Chebyshev points, these y values, and the appropriate degree. Okay, so here we have a coefficients of a Lagrange polynomial. So let's take a look at those coefficients. This will be of degree 49. Oh, I need to make it a column vector so we can see. Yeah, look how crazy these numbers are. Magnitudes all over a map. These last coefficients, we don't really have those very accurately. Because, so the thing is, when you're evaluating a Lagrange polynomial like this on the interval 0 to 1, where all the roots are, you're supposed to get some pretty small values, but you're obtaining those small values from adding and subtracting very large numbers. In other words, this is a big old catastrophic cancellation fest. So, so what this shows is that the conventional way of computing the weights for interpolatory quadrature, where you take the integrals of Lagrange polynomial, in the case where we get the coefficients in power form of Lagrange polynomial, which is what you see here, and then we just carry out, analytically the power rule for integration, and you plug in the limits. That doesn't work so well when you're doing a high degree Lagrange polynomial like this, and that's why. So what this means is these weights here are not the correct weights. There's way too much round-off error involved in their computation. So this poor result that we got for Clenshaw-Curtis quadrature, this is not what properly implemented Clenshaw-Curtis quadrature would produce. So on the other hand, if we used this formula is given here for computing the weights, then we would get a much better result because those weights would turn out to be positive. Right, so it's important to keep in mind how the various quantities involved are computed. So using Lagrange polynomial power form coefficients to get the weights is perfectly fine when you are at lower degree. But once these coefficients get out of hand and vary over several orders of magnitude, it doesn't work so well. So there's all kind of pitfalls where round-off error can get you. So questions on what happened here? So Clenshaw curves did work up to a point, but this just didn't amount to a good implementation. All right, now I can turn to the intended topic for today, and I spent all my time in Newtoncotes because I actually don't have much here in the way of notes. Okay, and really the point of this section is to deal with what we've just been seeing. That if you want to get high accuracy by using more quadrature nodes, using high degree interpolatory quadrature is generally not the way to do it, unless you're very careful selecting the nodes, and very careful in computing the weights, as we've just seen. But there is a better way, that's called composite rules. So what we do here is you take the interval AB that you're integrating over, and you divide it into subintervals. And on each subinterval, you use a low degree quadrature rule, such as Simpsons Rule or trapezoidal rule. Okay. Now, as we saw in Newtoncotes rules, I showed you error formulas for those. the error is always proportional to some power of b minus a. So if ab is large, that can get large. And there's also a higher order derivative of f involved, which can also get large. Um, so, but if the interval you're using a Newtoncotes rule on is small, then you have a power of some small value that will keep the error small. So here I'll show you a few examples of composite Newtoncotes rules. So what I'm doing is dividing AB into n subintervals. So here's the width, equal width. Here are the endpoints of each subinterval. So here are the formulas for the endpoints of these subintervals using the spacing. So so x0 would be a, then x1 would be a plus h, x2 would be a plus 2h, and so on, and b being the last point. All right, so n subintervals, n plus 1 points in total. Now, the first rule, composite rule I'll show you, is the composite midpoint rule. So we have two midpoint rules. There's this plain midpoint rule that has only one node in it. It's the midpoint of AB. And then there's a composite midpoint rule where we're applying the original midpoint rule on subintervals, or in this case, think of pairs of subintervals. Um, so what I'm doing here is my first subinterval has width of 2h, and here's the subinterval, x0 to x2. So then its midpoint is the first node in my composite rule. And then I go to the second subinterval that has a midpoint of x3 for my second node, and so on. So really I'm applying a midpoint rule to not one of these subintervals, but pairs of subintervals. So and notice I'm only using the odd numbered points. So I have n plus 1 points in total, but I'm only using about half of them in this rule here. Um, so then what I would do is use use the error formula for a midpoint rule, which from before was second derivative at an unknown point um, divided by 24 times b minus a cubed. Okay, actually going to bring that back here so you can see how this error formula comes from the other. Okay. Okay. Where 8 is an unknown point in the interval. Um, okay. Um, and keep in mind here, this relationship b minus a is equal to n times h. Okay. Um, now, um, so what I'm doing is I have a sum from 1 to n minus 2 because I'm taking, I have n subintervals in total, but I'm using them in pairs. So I really have n over 2 applications of a midpoint rule. So I need to use this error formula n over 2 times. So I'll go ahead and copy that in here. Each subinterval has its own unknown point for a second derivative. And then the width of a subinterval on which midpoint rules apply is 2h because I'm using pairs of the original subintervals. And now I have to add all this up. Okay. All right. So now what I have is, so I can pull certain things out of a sum. So I'm going to wind up with 8h cubed over 24, or that simplifies to h cubed over 3. But then I have a sum of second derivatives at unknown points. But by the intermediate value theorem, if we assume that f double prime is continuous on the interval AB, I can replace this by I can replace these by an average at a single unknown point, and then times n over 2. So this is the same as 3 times n over 2 times f double prime at a single unknown point, again by intermediate value theorem. And then n times h is b minus a. So then I get b minus a down here. I still have h squared left over. That goes here. 2 combined with 3 to give me 6. And that is my error formula. Okay. So these manipulations here lead to this error formula here. Okay. Now, that's one way to describe the midpoint rule in terms of the subintervals that I had to show that it really is a midpoint rule. But then I have all these other points, x naught, x2, x4, the even number points that I'm not using at all. So, so a more sensible way to describe the midpoint rule is this way, where we have n subintervals as I originally defined them, and then we take the midpoint of those. So now we're using n subintervals, each of width h. Dang it. Okay. So that's the composite midpoint rule in that case. And so, and then this is a resulting error formula. So it's almost the same as we just have a different factor down below. Okay. Because now the midpoint is being applied on an interval that is half the size of a previous case. So this is how it's commonly written. Now, so what we see here is the error is order h squared. So if you use the composite midpoint rule to evaluate a given integral and use a certain number of subintervals, and then you double the number of subintervals, then the error should decrease by a factor of roughly 4. Or that, to the extent to which it happens depends on how the second derivative behaves. So that's what we mean by second order accurate. So similar to what we saw with numerical differentiation schemes, it also depended on a spacing h. And you see that the error is big O of a power of h, so that's the order of accuracy. Next is the composite trapezoidal rule. So what happens here is on each subinterval, like x0 to x1, x1 to x2, etc., you're using a regular trapezoidal rule, the Newtoncotes rule. And if you add all of those applications of a trapezoidal rule for each subinterval together, then this is what you get. And notice that all of the function values are multiplied by 2, except for the first and last. And this is because each of the interior points are used in 2 trapezoids. So the first trapezoid involves x0 and x1. Second trapezoid involves x1 and x2, and so on. And here's another way of writing the composite trapezoidal rule. You have f of a, f of b, and then twice the sum of all the other f values in between. And then similar for Simpsons rule, where you are using, here it's required that n is even, and you're applying Simpsons rule on each pair of subintervals again. So here we have a first application of Simpsons rule using the points x0, x1, and x2. Then the second application of Simpsons rule would involve points x2, x3, and x4. That's why, once again, we have a coefficient of 2, because remember, for Simpsons rule, your weights had this pattern of 1, 4, 1. But because this x2 is shared between this application of Simpsons rule and this one, it needs a coefficient of 2. So the pattern of the coefficients is 1, and then 4, 2, 4, 2, 4, 2, etc., and then 1 at the very end. So what you can see is that the amount of computational effort involved for composite Simpsons rule and composite trapezoidal rule is exactly the same. We're just multiplying these f values by different coefficients. And the error for Simpsons rule is proportional to h to the fourth. So Simpsons rule, composite Simpsons rule is fourth order accurate, by contrast to midpoint rule's second order accuracy. And because of that higher order of accuracy, it depends on a higher order derivative. So if a function is not 4 times differentiable, then this rule might not be so accurate. So that's something to keep in mind is, does the function you're integrating actually have the derivatives that are required by the error formula for whichever rule you're using? If not, then you can't really expect the order of accuracy to match. So for instance, if f is not 4 times differentiable, actually continuously differentiable on the interval AB, you can't expect fourth order accuracy, unfortunately. Now, you might have noticed that I've shown you the error formula for composite midpoint and composite Simpsons. I've not done so for composite trapezoidal. And that's because I have it worked out down here. So this is the same approach I used for midpoint rule, but I figured it would help since the first one was not planned. That it'd be helpful to see it done here. Okay. So for a composite trapezoidal rule, I'm using the basic or Newtoncotes trapezoidal rule over n subintervals. So I'm adding up the error from those n subintervals, and that's the error formula here for the Newtoncotes rule, where we have f double prime at a different unknown point for each subinterval times minus h cubed over 12. Well, before it's b minus a cubed, but in this case, we're applying it on an interval of width h, so it's h cubed here. So then what I do is I go ahead and pull out what I can, the minus h cubed over 12, and then I multiply by n over n. And the reason for that is an n in the numerator, I pair with one of the h's, and that'll lead to a factor of b minus a, and then times h squared. And then the other, I lump in with a summation. So what I have here is an average of values of f double prime. at unknown points from each subinterval. And by the intermediate value theorem again, there exists a point in AB such that f double prime is equal to this average of our f double prime values. So then I can replace this by the value of f double prime at a single unknown point. And then I still have this factor of minus h squared b minus a over 12. So for all of these rules, composite rules, once you have the error formula for the Newtoncotes rule on which it's based, then you just go through this process to figure out what the error formula for the composite rule is. So we see that both the composite trapezoidal rule and the composite midpoint rule are second order accurate. But as in the case of the Newton-Cotes rule, the error for the midpoint rule is roughly half that of a trapezoidal rule. Now, interesting side note about the composite trapezoidal rule was that, and this was developed a very long time ago, but more recently, I unfortunately can't recall exactly when, it was like accidentally rediscovered in a biology research article where the author needed to essentially compute area under a curve. And so what they did was approximate the area by trapezoids and then add up all of those. And not being aware of the existence of a composite trapezoidal rule, named a method after themselves. So there was a something like Tai's method, TAI, and this one that was equivalent to the composite trapezoidal rule was named like the improved Tai's method. And they just didn't know. And what happens is these papers get peer reviewed by people in that field who also might not be aware of it. But at some point it was discovered. So it's become an alternative term for composite trapezoidal rule. So depending on what field you're in, but that's the thing that happens sometimes that peer review can catch a lot of things, but not everything. Okay. Now, so one of the interesting aspects of these composite trapezoidal rule formulas is that because from the error formula, it may be possible to figure out how many subintervals you should use to get a certain level of accuracy. And so I have an example in the text about that. So I'll go ahead and show you that. Okay. So my pet example, integral from 0 to 1 of e to the x. Suppose we want to use a composite rule and get be assured of having an error of less than 10 to the minus 3. So essentially 3 decimal places correct. So what we could do is we could take this error formula and we can require that in absolute value, it must be less than 10 to the minus 3. Now, in the case of the exponential, you go ahead and fill in a derivative, the second derivative, and then fill in a and b. So then the error formula in this case becomes this. Now, I've also kept in mind that h is equal to 1 over n in this case. So in general, h is equal to b minus a over n. But I want to express everything in terms of just one variable, n, because n is the number of subintervals I'm looking for. Now, the point eta is unknown, but I know it's between 0 and 1, so I just pick a value of eta that will make this the largest. E to the x is increasing, so this factor, this numerator cannot be any larger than e. So I go ahead and fill in e. So now I have this bound for the error, in terms of a number of subintervals n that I'm looking for. So then I go ahead and take this inequality and solve it for n. So as long as I choose n at least 16, then I'm guaranteed to have error less than 10 to the minus 3. Now, generally, this is a pretty conservative estimate, so I almost certainly could choose n to be even less and still get that level of accuracy. But again, we're looking for a guarantee. Now, if I want to do the same with Simpsons Rule, so same kind of situation. Here's my error formula for a composite Simpsons rule. So I specialize it for the function and interval that we have. So now if I do the same thing, I said this an absolute value less than 10 to the minus 3 and solve for n, then this is what I get. N must be, so I could choose n equal 2. So in other words, I don't really need to use composite Simpsons rule at all to get error less than 10 to the minus 3. I could use the basic Simpsons rule, just using these free nodes. And sure enough, I do get these decimal places correct. Okay. So questions about any of this or on homework? We have time.
Good luck tomorrow.
Oh, thanks. Well, fortunately, giving a presentation I've given before, so I'm not too worried about it. But yeah, it'd be nice to. I've never really spent time on Mississippi State's campus, so it'll be interesting. So, but again, even talking to you before can be stressful just because with a new audience, you never know what questions you're going to get asked, and sometimes they're kind of off the wall. Okay, I guess that's a wrap.